Hi, students. This is Mrs. Foy, and I just happen to have my husband here with me today, Dr. Foy, who is a PhD in analytical chemistry. So he knows a thing or two about electrons. And since we're both here, we thought it'd be fun to do this lecture together for you. So we're going to talk about the motion of electrons. And what do we know about electrons? Are they just moving randomly around the nucleus? We know a little bit about them, right?
We actually know a lot about electrons. We do know that they're not just randomly moving about the nucleus because they're in specific energy levels. And so they conform to these specific energy levels, so they can't have just any given energy at any given point. This is actually pretty fundamental to analytical chemistry because we look at the photons that are emitted, the photons that are absorbed, and that's one of the biggest things about analytical chemistry.
And you guys don't know about energy levels yet, but you will. But one thing you should know is that you know that these electrons are moving around kind of in an area that we call an electron cloud.
Right.
And so you'll learn more about that later. So there's a dude named Max Planck, and they're going to learn about Planck's constant, and they're going to do some equations with that. But I know that he discovered something really important that helps us understand the way electrons work, and that's called the photoelectric effect.
Yeah, the photoelectric effect is very interesting in that in normal, so this is one of the things that gets pretty complicated about electrons, and this is why we have to look at quantum theory. But in a normal situation, you would just pump energy into something, and eventually it would absorb enough energy that something happened, right? But not with electrons and metals. So, or electrons in any element. You could pump energy into it all day long, and that energy would not build up to result in ejecting electrons. You have to have what's called a threshold frequency, which is a specific amount of energy that you have to put into that system in order to eject an electron. And that was the photoelectric effect.
So it was that some metals showed this electrons emitting and absorbing light and some didn't? That was
it was that all metals would do this given the right wavelength of energy.
Oh, okay, so they got to that threshold.
Right, that threshold frequency. And we talk about energy of light. We often refer to a frequency because frequency and energy are directly related.
Right, and they're going to learn more about that. And they're also going to learn about these specific jumps that we know are called quanta. So that's what, that was one of the things that came out of this, right? Is that electrons, it looked like that they had just specific energies. They were just absorbing specific energies, and then they were emitting that on the way back down. And that was something that helped us understand the way electrons work.
Correct.
And too bad that we can't do this particular experiment this year. Hopefully you guys will next year. But we can take a tube of glass that has a vacuum in it, and we can put atoms of a certain element. And when we excite those, like plug it into electricity, we can get those electrons to reach that threshold and jump up. And
so it's not, okay. The threshold frequency refers to the amount of energy required for an electron to be ejected. These electrons aren't being ejected.
They're just getting
These
excited.
Electrons are exciting to different levels. And these different colors of all these different signs are associated with different transitions. And so when they absorb the energy, they relax back down because they don't want to be in the excited state, and they relax back down and they give off these different wavelengths in the visible spectrum, which correspond to different colors.
And are all of these colors neon? Are these neon gases for all of these different colors, or are they different elements?
You
for neon
can
lights?
use different elements, but you can also do you can excite them at different levels to get
Okay, to get the
different
different
lines out.
colors.
Because if we go to this next slide,
Right.
there's a difference. So if you look at that light bulb on the left,
This
right?
guy right here. Yep.
Yeah. That light bulb is emitting what we call white light, right? And that's a continuous spectrum.
Mm-hmm.
A continuous spectra is all different wavelengths.
Mm-hmm.
And the way you get that is through heating up something that will emit multiple wavelengths.
Mm-hmm.
A continuum then says on the right-hand side of that, you will get out all those different wavelengths. There won't be one specific wavelength that's coming off.
Mm-hmm.
Okay, so in other words, that light bulb has a bunch of different things in it that are creating all of these different wavelengths.
Right.
So you're getting that entire spectra at the bottom.
Right. And this prism is refracting those light waves, right? And separating them into the different Roy G. Biv colors that we see there.
Right. A lot like, the little sun catchers that you have in the window.
Mm-hmm.
When that comes through, you see all the different colors of light coming through there. Right. What you don't see is what we see in this next slide.
Right. And I guess I should point out this little bar down here is part of the electromagnetic spectrum. It's showing me wavelengths of light here, NM is nanometers, and this is just showing the visible spectrum. So it's not showing infrared would be over here, and UV would be, ultraviolet would be up there. So we're just looking at the visible spectrum.
Which is a very small part of
the whole spectrum, correct.
The entire electromagnetic spectrum.
But this is really cool, because this doesn't show, this is not a continuous spectrum.
Right. And this is where it gets much more complicated, because now what we're looking at is the spectrum for hydrogen. Mm-hmm. And hydrogen as an atom has only certain ways in which it will excite. Mm-hmm. And then that excitation results in emission. Mm-hmm. And so this is the emission spectrum of hydrogen. And all the black on there means nothing's coming through. Right?
Right.
All the lights on here are the different wavelengths of hydrogen relaxation. Mm-hmm. So you go back to that neon light.
Yeah.
The neon light, when you just have neon by itself, does this as well. Mm-hmm. So this spectrum, this electromagnetic spectrum, you can also look at this in terms of wavelength, and you can look at it in terms of energy. And so the different energies required to get, for instance, that orange versus the violet, those are different energies of excitation followed by emission.
But this is one electron. This is hydrogen's one electron.
That's correct.
And so it is that one electron is going up and falling back down in certain
patterns. Yes, it can be excited into different levels. Mm-hmm. Those levels can then result in relaxation to even different levels. So that's why you have multiple lines in there, and not just one single line. Right.
So in order to understand why this was happening, these physical chemists like Bohr tried to come up with a mathematical model to explain why specifically hydrogen made that pattern.
Correct.
And so even though this model we know is not the model we use today, it still explains.
Yeah, so I hate this model because what it does is it overly simplifies things. And when you think of the solar system, you think of the planets revolving around the sun in these very specific orbits. That's not what happens here. But this model is instructive in that what you can use it for is understanding these different levels with respect to the nucleus. So the nucleus is in the center there, right? The green thing.
Right.
And then outside of the nucleus, you have these areas of energy. And so the first area of energy is different than the second area of energy, which is different from the third area of energy.
Right.
And the distance from, that's why we use the solar system model. The distance from the nucleus is what's important here, because as you get further from the nucleus, it's harder for the nucleus to hang on to the electrons, right? It's harder for the protons to actually hang on to those electrons. So those energy levels, depending on which perspective you use, the energy levels are either increasing or decreasing. If you're an electron, you'd rather be in the third energy level because that means you can get the heck out, as opposed to being in the first energy level, which is where you're held the tightest.
From that quantum, from the Coulombic attraction from the nucleus.
Right, from the nucleus.
Right.
So they can go from those different levels, right? They can go from the ground state, which is the bottom, and all. What's really cool about this is once we get beyond hydrogen, it gets even more complicated. Ground state electron configurations change, and when it's in the ground state, it can absorb energy and be excited into an excited state. But I mentioned this before, electrons don't like that, right? They don't want to be in an excited state. That they have to give off that energy. And so when they give off that energy, they can relax back down to a ground state. And that's when you see these very specific lines, right? These wavelengths that are of a very specific energy.
Right. That's the photon, the quantum photon that falls back down that gives off that. So this is really cool, because then we figured out that we could actually look at different elements, and depending on their electron pattern, when we excite them, then their electrons would jump up to certain levels and then fall back down in a characteristic pattern and make very specific line spectra that we could use to identify. Like it's like a fingerprint, of this specific. And
when you talk about energy, a lot of times we jump back and forth with energy, and we talk about photons, but then we talk about heat, right? And so we're talking about, in general, the absorption of some energy value, whether it's heat, whether it's a photon, but it's the absorption of that energy by that specific element. So when you do the neon light, you're running a current through there, which those atoms are then absorbing that energy. A lot of times it's in the form of heat. Sometimes it's in the form of actual electrical signals. And so the energy is absorbed and then it gets emitted in these specific patterns. And it is a fingerprint for something like lithium. If you get a chance to do a flame test, right? You guys,
they're going to learn about that.
And they may have seen those before. But all these different elements, there's different colors coming up. And the dominant color is what you actually are going to see. But if you actually were able to use a prism and separate them out, you would get these very specific
And I guess
lines.
we should explain that this spectroscope is basically the prism. Right? So it's what's separating that light there. So so look at this, guys. This is so cool. So we've got sodium's emission spectra, mercury's emission spectra, lithium's emission spectra, and hydrogen's emission spectra. And basically what that allows us to do, I love this this special periodic table, right? Because it's basically like a barcode, right? So it's like a barcode of light energy that is specific for every specific element that we have in the universe. So this is how we can use instruments, right? And we can get light from stars and we can figure out what elements are on there, right? Because it's whatever the barcode is of that particular element. So that's how we know what are in these stars that are far, far away. It's so cool. So tell us about this, and tell us about these different series. And they don't need to know everything about this, right? What's the level
so what
that
you
they
need to know is that there are these different energy levels, right? There are these N energy
Right.
levels. And you're going to learn more about this as you get into electron configuration, but N is the electronic state that an electron is in. And that's the one that we consider for these kinds of emissions.
Right. And the nucleus would be down here, right? Because
Right.
N is equal 1 is the closest to the nucleus energy level.
And so then what you're looking at in these different series is the relaxation from. Okay, so in other words, you look at that Lyman series and you've got the relaxation where N equals 2 goes back to N equals 1. That corresponds to a specific jump in energy. B is 3 to 1, that's specific. C, 4 to 1, et cetera, et cetera. Then each of these series is the emission back down to a different level. So a hydrogen atom, the electron can actually relax back down to any one of these levels once it's excited. So
doesn't
it can
always
relax,
have to be back to.
It doesn't always go back down
1.
to the ground state. Right. It can be stabilized for some amount of time in any of these other states. And so you've got the Balmer series, the Puget, et cetera, right? And that's just the relaxation back down.
That's cool.
So then those all correspond to very specific wavelengths, right? And so, for instance, that first set that we were looking at all the way over on the left, those are all UV. So you can't see that.
Ah, right.
So the Lyman series, you can't see it.
Yeah.
The Balmer and the Passion series, both of those are in the visible region.
In the visible region right here.
But then that other series is too low energy.
Too low energy. This Passion series
is too low energy, and that's out in the infrared. And then the Bracket series goes even further out. That's actually probably into the microwave or even the radio frequency levels, right? So the only ones that we can see, the actual line spectrum that we can see using the spectroscope is that Balmer series.
The Balmer series. That is so cool.
And the other thing you can notice about this is if you go from left to right, 3 to 2, right, is going to be the lowest energy transition because the gap between 3 and 2 is the smallest. 4 to 2 is going to be a little higher energy. And so if you look at these wavelengths, you go from 656 up to 486. 486 is a higher energy wavelength or a higher frequency wavelength, however we want to describe it.
And we'll learn about this tomorrow, that the shorter the wavelength is, the higher the energy level is.
Correct.
So that's why he's saying higher here, even though it looks smaller. It's a smaller number because it's a smaller wavelength.
Right.
Cool. So that's what you just explained here, right? So these energy levels, and we're going to learn about these energy levels, that they fall in very specific patterns. And there is a very crazy kind of math called quantum mechanical theory that explains these mathematically. And they're not going to need to know that for this class, but they are going to learn how to be able to show the pattern of where these electrons are.
Well, so if you think about this, what we're exploring right now is the absolute simplest model you can have. One electron, one proton.
Right.
That's it.
Yeah.
So you got nothing other than that proton-electron interaction to worry about. Quantum mechanics has to explain all of the electrons in all of these different configurations. And that's why it gets so complicated. There was a slide back there where it showed you an energy gap for the hydrogen atom. It's a fixed energy gap, right? And so you can look at the difference between those energies and get out the wavelength of interest. The more complicated the system, the more you can't do that. The more you have to worry about all these other interactions. You put a second electron in, and that second electron affects the first electron, which affects the protons, which affects all
which is why Bohr's model worked only for hydrogen. And we needed that quantum mechanical model to explain everything other than poor little old hydrogen with just one electron. So this is what you were explaining in that other slide, right? That's a very specific type of series that allows us to see only in the visible range. And those other series are either too small of wavelengths and we can't detect with our eyes, or
Higher
too
energy
long
or
of
lower
wavelength
energy.
to be able to see.
Right.
All right. Well, thank you, Dr. Foy. I learned a lot.
You're welcome.